Okay, so the idea here is that if I give you something like, say I told you I had the integral of what was the one I was doing in class earlier? X squared minus y dx plus 2xy dy. So you have m, you have n, you have f too, because f equal to mn. M and n are the components of f. And so you're basically saying like, oh, I know what the vector field is. The vector field is the vector field that has x squared minus y in the first component and 2xy in the second. So you can always go backwards. I mean, the reason why people like this form is because it holds all of the same information that this does, but it also pre-computes exactly what's going on in each direction.
I went back and I substituted dx for like the x partial of the path.
Yeah.
And
Yeah, no, so here, like the idea is once you choose your path, I mean, you're still going to be using here that dx is equal to x prime t dt and dy is equal to y prime of t dt. You do need to use those if you actually want to compute the value of this thing. But yeah, you need to read f off of this.
yeah, okay.
Sorry. All right.
What is it?
It's most important, somewhat important, least important, not very important and least important. No, this is, I think somebody is trying to help somebody think about how to live in their future. Oh, I have this enormous stack of homework for you guys to dig through. It may be distracting for me to hand it out. Do you want me to hand it out and let you pass it around, or do you want me to wait till the end? All right. Okay, so right, does that make sense? Like that you get the F? Yeah. So is there anything else? Okay, yeah. So this is supposed to be I have lots of math to talk about. I do, but I'm also happy to talk. We have an exam tomorrow, I believe, so we can also talk about that if you want. No, we're thinking about the way that you should be thinking about m and n is that m and n are the x and y components of the vector field. There's no other way to think about it, right? So m, we think about, just by definition, the only thing the symbol m means. So when you think about m dx is the contribution of the vector field in the x direction. And then you take that and you add it to the contribution of the vector field in the y direction. And you add those together and you get the total contribution of the vector field in the direction of motion. That's really kind of what the interpretation is. But you should be thinking about f of x and y as just by definition being m x y comma n x y. So these are just the functions that tell you what the arrows look like as you slide around in your vector field domain. Right, so it's the way that tells you the m and the n basically give you how the force field varies as you slide around inside the domain. 5.5 number 8. Okay. Wait, I don't want these. Oh, my eraser. Okay, so can you read off the integral to me? It's the integral from 0 to 1.
From
And the
y over 2 to y over 2 plus 2.
And then the function was
2x minus y dx.
x minus y dx dy. And the question says?
Evaluate the integral to sketch the region D of the integration.
Okay, so what is the region of integration? So these things, so one way of thinking about approaching this thing is to think, what variable are we integrating with respect to? Well, we're integrating with respect to x first, right? This is an iterated integral. So we think, this is an x integral. And so those are x values. And so really what I'm doing is I'm integrating from x equals y over 2 to x is equal to y over 2 plus 2. And so I need to sketch this region. Oh, and also and these guys are y values, right? From y equals 0 to y equals 1. Well, maybe you're not good at drawing lines that are x in terms of y, but you could still sketch these like this. Right? This line is the same as the line y equals 2x, and this line is the same as the line y is equal to negative 2x plus 4. Right? No. Yeah? No, x minus 2. Okay. 2x minus 4. Make sense? Okay, so let's just sketch that. So y equals 2x is a line that looks like this. And y equals 2x minus 4 is a line that looks like 1, 2, 3, 4. That looks like this. Where does it cross through the x-axis? Where's this point? 2, 0. And it says we want to integrate y values that start at 0 and end at 1. So this region right here is what we're integrating through. Because we're going from this line to this one, which means we're going from here to here. And y values that go from y equals 0 to y equals 1, which means we took these y values and then we cap off right there. So that's a picture of what that region looks like. And the easiest way to draw it is to translate these things into the typical y equals mx plus b setting, and then just sketch it that way. Carve out the region. All right. Okay. Then what are you supposed to do? Integrate it probably, right? Right.
Yeah, give u and v. And then
It gives a u and v. Oh, what are the u and v?
2x minus y.
U is equal to, okay, so 2x minus y is equal to,
u.
and
V is equal to
y is equal to v. Okay. What does that do? Well, we have to change the region over. Now, first question, is this one of the things I asked you guys on your review is identify a linear change of variables. Is that a linear change? Yes, because it's just a combination of scalars times variables, right? There's no product of variables here, which means if I want to translate one domain into a different domain, I just have to keep track of where the corners went. It's the nice thing about working with regions when you have a linear change of variables. This is a linear change. So let's see what happens. Okay, so this is D. And the new region that we're going to be working with is, well, where does 0, 0 go in this change of variables? So if I took x, y is 0, 0, where does that end up? What's the u? Right? How about, what's the next corner here? 2, 0? Where does 2, 0 go? What I'm doing is I'm taking 2, 0, and then a 0 right here. So 1, 2, 3, 4. Where is this point? So that point is asking you, that you can identify that point by saying, for what value of x is y equal to 1? So this point has coordinates 1/2, 1. So if I want to keep track of what happens to that corner, that goes to 0, 1. And then the last corner is this guy out here, which is probably what, 3/2, 1 is what I'm getting my guess here. This is 3/2, 1. Where does that go? 3 minus 1 is 2, 1. 5. What did I do? Oh, 5/2, 5/2. So that's 4, 1. Oh yeah, 5/2. I should have known better. 3/2 is not to the left of 2, but 5/2 is. Okay, so that means that this box is what comes out here. It's like, man, that's a nice change of variables, right? That kind of sucks to integrate over. This is pretty nice. It's just rectangle.
So, it is linear change because the combinations of X and Y, which is.
Anytime you see combinations that are just, so this is a linear combination of X and Y is equal to U, and a linear combination of X and Y is equal to U.
And if it's not linear, you cannot do it.
Yeah, this doesn't, you have to be careful about what happens to the actual curves. If you have curves involved in those change of variables, that these things could be like exponentials or quadratics or something like that. I'm not going to ask you about nonlinear change of variables except for polar changes. You don't have to do any of this computation for them. Okay. Yep.
What if you're given like X and Y from the integral aren't lines? So you're gonna give a link to those two.
What do you mean?
As in like if the integral was from like negative X squared to X squared.
So I could do, I'm not going to do that for this kind of question. I might do that for a polar region where you take a region and reinterpret it as a polar region. I would feel free to use pieces of circles. I'll do an example of that after I'm done with this one about what I might expect you guys to be able to read off the graph if I did that.
But if you give us a linear change, it's gonna be like straight.
If I give you a linear change, it's going to be straight lines to straight lines. Like the idea there is I've got to be able to give you something at the end that's easy to integrate, right? I'm not trying to test your theory of integration. Okay, so am I ready to work with this thing now? So this right here, this calculates the new region. This is sort of P of B. So I'd really like to integrate this in my new variables, Y or like U and V, and I can probably, without doing anything else, I could write down the U and V limits of integration right now. That's very easy to do, right? Because I could say, oh, well, I'm going to integrate in the U variable from 0 to 4 and in the V variable from 0 to 1. So at least I got that part of the theorem down, right? It's the integral, and I should probably put, say, we'll go from 0 to 4 du, and from 0 to 1 dv, because these were UV coordinates. Yep. We have not calculated the distortion factor yet. I'm saving the calculation of the distortion factor because there's two ways to do it. Okay, so let's change so just to anticipate the fact that we haven't done that yet, let's remind ourselves that we're going to have to put dx, y, duv right here. I'm going to have to compute this Jacobian to calculate the distortion factor. But the function is pretty easy under this change of variables. What does the function become? Well, just u. That's all there is, right? I mean, that is a u. Man, what a nice integral. It's like your calculus professor, your vector analysis professor went out of his way to make sure that the integral that came out the end of this is trivial. Now what? I got to compute that. What is it? And be careful because there's a major landmine here.
You have to find X and Y in terms of U and V.
So there's two ways to do it. You can find X and Y in terms of U, and this basically says you must know X and Y as functions of U and V to compute. But there's a cheesy trick you can use if there's linear equations. So I'm sort of reluctant to give you the cheesy trick. So if you know the cheesy trick, which requires remembering from linear algebra that the determinant of the inverse is 1 over the determinant of the original matrix, and if you don't know what I mean, then just pretend I didn't say that. To compute the Jacobian, you have to actually change variables, which means dx, y, duv is this determinant. It's dx du, dx dv, dy du, dy dv. But I can't calculate that, or the determinant of that. But I can't calculate that right now because I don't have x as a function of u. I have u as a function of x and y, and v is a function of y. So I've got the backwards formulation for what I want. If I want to compute this Jacobian, I have to solve for x and y in terms of u and v. Now, the nice thing about these linear change of variables is that's trivial, because you can always just add these things together. Like, notice that if I carefully add these equations together, I get 2x is equal to u plus v, which means x is equal to u plus v over 2. And this one is already solved for you. If v is equal to y, then y is equal to v. So that is the set of equations that needs to be plugged in up here, because the Jacobian has to have the u and v that you're taking derivatives with respect to. Okay, so everything about this is really nice, except for the part where you have to invert the relationship to calculate the Jacobian. That's equal to the determinant of, okay, dx du is 1/2, and dx dv is 1/2, and dy du is 0, and dy dv is 1. So the determinant of all this is 1/2. Now, if you're willing to squint a little bit, you might notice that if you calculate the Jacobian of this thing, you get 2. If you calculate the determinant of 2 minus 1, 0, 1, you get 2. Now, if you have no idea what I'm talking about, don't even look at this. In fact, just pretend I didn't say that. Pretend I did not observe that this is 1 over this. And instead, when you get a problem like this, right, this is the rule I think you should follow unless you really understand what's going on with linear algebra. What you should follow with this rule is, if you get a substitution like this, invert it into x and y. So take the substitutions u and v, invert them to get x and y as functions in u and v, and use that to calculate this determinant. Okay, and you won't go wrong if you do it that way. And that means we're ready to put the integral together, because now I know what goes here. This is the integral from 0 to 4 of the integral from 0 to 1 of u times 2 dv du. And it's likely that I might ask you to actually run through an integral like this all the way down, just to see if you guys remember how to compute iterated integrals. Okay. It's not hard, but yep.
Probably missed it, but I see why you say u is 2x minus y, but y is v y.
Oh, because I said it in the original, because they gave me the substitution at the beginning. They just gave, this was given to me. So basically the game I have to play with substitution is, I basically have to, if I'm going to give you anything complicated like this, I have to tell you what the substitution should be, if it's going to be anything at all, that like, I want you to work through the whole process, right? I mean, it's not obvious to me that this is the right, finding the right substitution is difficult. It's not something I think that necessarily I'm going to, if I put on a test, it's like, I kind of have to tell you, use this change of variables. Here's an integral. I mean, I erased it, but you know, here's an integral. Use this change of variables to evaluate it. And that would mean that you could walk through this whole process, but you wouldn't be guessing what the substitution is. I'm gonna, if I have a problem like this, I'm gonna tell you, I'm gonna get, this will be written on the page in the problem. If this is not an obvious choice to do this move, right? It comes in the statement of the problem. I mean, the reason I suggested these problems is because this is information that was given to you as part of the exercise, was here's the change of variables, go ahead and walk through the process of doing this. And anything more complicated, where you get like some really nasty object right here, I'd have to tell you, this is the, like, just set the integral up, like something I asked you to do. Because in that case, in a more complicated problem, it might be really hard to reverse the variables. That's really the issue, is that like finding the substitution is actually the hardest part of these things. And all I'm really testing if I ask you to do that is, did you get lucky enough to stumble on the right answer? And that's not a lot of technique there. Certainly not for a 50-minute exam. Yep. Sure. Well, let me go here first. Oh. 1/2. It's the same number that came out here. It was just my bad. It was 1/2.
So when you're switching from in terms of x to terms of the integral, you want to be Jacobian with x, y over 0.
Yes. And that, so in that, it's important in the symbol, when you write down the, so the way that that theorem is stated is like this: the double integral over d of f of x and y dx dy is equal to the double integral over t of d of f of x of u and v, y of u and v, Jacobian of x, y with respect to u and v, du dv. So it's written into the actual like definition of this change of variables formula. You need x and y as functions of u and v. Yep. Yes. Yeah, I'm not going to ask you guys to, I mean, that's not a test in matrix multiplication, right? So now I may ask you to, if I ask you to do a simple linear approximation, I might ask you to try to work it all the way out, but probably not, right? I mean, certainly not at the function level. Like, I might feel comfortable saying, plug 1, and I think I did this on the last test, plug in 1 and 2.1 and see what can tell me the number that comes out. But that'll just be like, can you multiply 2 by 2 matrices? So like that would be all, I would specify in that question for full credit, make sure you give me a single number that represents the output. Yep.
There's like one, there's like something in the, but it had to do with like the cylinder and like the can volume and like kind of if you don't want the volume itself to change, but the radius is changing, like how to do the height change. And I know we talked about it with the red ball, but I was just wondering if you
Yeah.
do similar.
Yeah. So the idea of that exercise was, do you remember the specific exercise that I gave you for that one?
37.
37.
Yeah.
Yeah. 1.
All right, 1 second, let me pull it up. 37, you said 4.1? Oh, jeez. I hate these things. Come on. No, that didn't do it. There we go. 4.1, 37. Okay. A can of mushrooms is currently manufactured, a very specific question. A can of mushrooms is currently manufactured to have a diameter, so it's got a diameter of 5 centimeters and a height of 12 centimeters. The manufacturer plans to reduce the diameter, so we're going to do a change in diameter of, not change it, we should probably do this in terms of radius, but for now, let's say it in terms of diameter. So the change in diameter is supposed to correspond to minus 0.5. And we want to figure out what the change, and we're going to try to estimate what the change in height must be to keep that the change equal to 0 is the idea of the question, right? Okay, so what I'm working with here is the volume of a can. That's really kind of what we're going to keep the volume the same. So the formula we're going to start with is the volume of a circular cylinder, which is V is equal to pi r squared h. Okay, so I should probably go through and rebuild this problem in terms of radius instead of diameter. So let's let r be equal to 2.5 centimeters, and we'll let the change in diameter be delta r is then minus 0.25. Does that make sense? So I can use this formula. I don't want to reconstitute. I mean, if I put like diameters in here, I've got to divide by 2 over, and that sucks. Okay. So how do I change? So I have to express this thing. Now what I'm thinking is I'm thinking of this as a function, volume as a function of radius and height. And what I want to do is I want to compute the total differential df at the point 5, not 12, but sorry, 2.5, comma 12. Radius 2.5, diameter, or height 12, right? So let's do that real quick. How do I do df? Well, the expression for df, the useful expression for df in these questions is df should be change in volume with respect to radius evaluated at 2.5 comma 12 times change in radius plus change in volume with respect to height evaluated at the point 2.5 12 times change in height. That's how you compute the differential. The differential is what's the derivative of what's the radius derivative of this function at this particular point, and what's the height derivative of this function at this particular point, and then that will give us a way of like wiggling r around and wiggling h around in balance with each other. So let's actually compute this. What is dv/dr? dv/dr is 2 pi rh. And if we evaluate that at the point are at 2.5 12, then we get 60 pi. I think. Does that seem right? 2 times pi times radius times height should be 5 times 12 times pi, which is 60 pi, I think. Okay, and now let's compute dv/dh. dv/dh is equal to pi r squared. And if I evaluate, oh man, I don't want to evaluate this at 2.5. I don't feel like it. 2.25 pi. 6.25 pi. 6.25, yeah, 15 squared is 225, 25 squared is 625. Okay, that's when I evaluate by plugging in the 2.5 in for R. So what does the differential say? DF says the following. At the point radius 2.5 and height 12, the way that I look at how the volume changes is 60 pi times change in radius plus 6.25 times change in height. Oh, there's pi here. So the question is, first off, what is the volume more sensitive? This is the what is the volume more sensitive to? Clearly, change in radius makes a bigger difference, right? Now that makes sense because radius in this formula is squared. So changes in radius are going to have outsized impacts because of the squared nature of the thing. Okay, so this is definitely more like quite a bit more sensitive to radius. And what is the relationship between what's an equal change in radius and an equal change in height worth? Like what's the factor of multiplication between these two things? It's sort of annoying 60 divided by 6.25. So it's about times 10, right? It's about, this is about 10, for every change here, right? You need 10 times the change here to make up for a change here. So what the problem in the original case, it says, well, we're going to lower the radius by about 0.25. How much, just on the level of estimate here, knowing that it's a times 10 relationship, if I lowered this by 0.25, how much should this have to go up by to make up for it? About, so if I drop this, if delta R is going to be minus 2.5, and I don't want the change in volume to be, I don't want it to move. I want this to be 0. Right? Change in volume should be 0. I'm going to lower the radius by negative 0.25. What do I need to increase the height by to counteract that? And the answer is the change in height should be about equal to 2.5. This small change in the radius can be balanced by this relatively large change in the height. Does that make sense? There's just proportionality going on. I mean, essentially what I'm doing is I'm saying this is about a times 10 relationship. And if I gave you a problem like this, I would strive to make sure it had integer answers so that we're not throwing 6.25 around and estimating. Although in real life, people just estimate. I am not, if I'm going to give you an equation to work with, I mean, you should not be hung up on the idea that I'm going to give you, if I give you a basic volume shape or something like that, you don't know it, just ask and I'll tell you. Like this is, I don't care if you carry this around your head, right? That's going to be another point because they don't remember how to calculate the volume of the cylinder, right? You know, I'm going to give you, if it's a more complicated equation, I'll give it to you. If it's not a more complicated equation and you just don't remember it, just ask. Like, how many of you guys know how to calculate the volume of a cone off the top of your head? Honestly. It's this, but with a 1/3 attached to it. Right? Like hardly anybody has that in active memory, right? So if I ask you about a cone, I'll just give you the, you know, I'll either write the formula down. I mean, the book doesn't, it's not my question, or I would have written the function.
I had a question on 5.4 as well.
Okay.
Number 21, you're setting up your own triple integral. I'm kind of confused on how to know the order, like dx, dy, dz.
Okay, so triple integrals, it's extremely unlikely that I'm going to have you guys compute a volume of triple integral off the on this exam that requires visualizing what's going on in 3 dimensions. Like I screwed this up in office hours when I was trying to show somebody how to do it. So the question you're referring to, I think, is the one where, I mean, I'm going to give you the idea because it's possible. I mean, I might ask you to compute one. What I'm saying is it's unlikely I'm going to ask you to visualize a region and then build it. We didn't spend a lot of time doing that. It's very computational, right? The idea there, I think this is the one where it's like, you know, what, y equals x squared, y plus z is equal to 9 in the xy plane or something like that. Is it this one?
I don't think so.
Okay, which is the one you're referring to?
It's like volume of solid bounded by z equals 4 minus x squared.
Yeah. So that's the one that has a cylinder cutting through a paraboloid, right? Again, not something I want to like push people on in the exam. We didn't spend time talking. triple integrals are really computational, and I want to spend time talking about conceptual questions and also things, simple computations. And the triple integral stuff is important, but it's important more for what we're going to do with it conceptually when we do Stokes theorem than it is, can you write down exotic shapes in 3 dimensions and visualize how they cut through each other? I can't do that on a 50-minute test. I'd be happy to show you how to do that in my office, but I cannot ask you to do a 3-dimensional volume like that where you have to visualize the surface. Okay, so, yep.
Kind of moving over to like local minimum maxes. When we're trying to find like the what kind of point
To
it is.
characterize in terms of the Hessian. So let me tell you exactly what it's going to look like when you see that. Okay, so let's talk a little bit about local maxes and mins. Okay, so this is the Hessian test for characterizing local maxes and mins, right? So the Hessian test. What exactly am I going to give you? So the first question is, are we allowed to do it the way that Colley does it with the determinants? And the answer is yes. If you really want to do it that way, you can. Okay. That was like, and if I'm going to do that, I'm not going to give you 3 by 3 determinants. The whole idea is to give you an interesting question. I can't give you anything in 3 variables because I don't really want people sitting around for 10 minutes computing a 3 by 3 determinant. It's really annoying, right? Because nobody would do that. You do it with a computer, right? So like, why hand calculate some determinant test? The idea is that if you have the Hessian, if you have HF of A, and say it's a 2 by 2 example here, fxx, fxy, fyx, fyy. And you want to do it the way that Colley does it, which a lot of you did on your homework. And the way that you do it is you test to see, is this positive? And is the determinant of the whole thing positive? So you say, okay, is fxx positive and is fxx fyy minus fxy squared positive? If they're both positive, what that means really secretly is that this diagonalized into a matrix where these numbers were both positive. So what will I tell you? I'm going to give you, so I'm going to ask you to compute a Hessian, and then I'm going to say, hey, by the way, here's a couple of matrices that if you plugged in this value of A and this value of A and this value of A, this is what the eigenvalue representation would look like. So if you want to do Colley's way and compute these 2 determinants and say, that's positive, and so therefore I'm at a local minimum, you're also going to have written on the exam this thing that's going to say at the value A is equal to 1, HF of A diagonalizes into this. Tell me from what you're looking at here what the solution is. If this number and this number are both positive, that's the same thing as saying this. These 2 eigenvalues being positive means it's concave up in both directions. The eigenvalues tell you what the concavity actually is. 2 positive eigenvalues means concave up in both directions. Where you'll have that written on the page somewhere. Okay. And if there's more than one maximum or minimum, I do not preclude the possibility of including too much information in that section. So you have to choose which is the correct diagonalization based on knowing which A value you're looking at. But again, the idea would be to say, what if you were looking at what does a local maximum look like? Well, a local maximum says all directions point down. So if the first thing is negative, but the determinant of HFA is positive, then you're looking at a local minimum, or sorry, a local max. Now, why should that be? Again, the reason I don't like this particular formulation is because it doesn't tell you why what's happening is happening. The other way you can do it, so you can compute it this way for a local maximum, or you can look at the matrix that I give you, and you look at this, and if these are both negative, both of the eigenvalues being negative means you're concave down in every direction, which means you're at a local maximum. You have to learn one of the 2 ways. Yep.
Do you just remind me if they're like 1 positive, 1 negative?
Yes,
So we can say, or is it like?
No, that's a saddle point is what that's called. So if you have mixtures of eigenvalues, that means in some directions it points up and in some directions it curves down. So if you got through to the end, now in Colley's test, that would look like if this is, if this is positive and the determinant is negative, then they have different signs. And if this is negative and the determinant is positive, then they have different signs, right? Which is annoying. It's like if you do the cofactors and they alternate in signs, then you have different signs in the eigenvalue. No, sorry, if they're both negative, sorry. Yep.
If we get the values are zero, we have to further clarify.
No, I want you to know what it means to have eigenvalue 0 to be able to explain what it means. If you did a determinant test like this, a Hessian, and you got that the Hessian was equal to 0, like you compute the determinant. Let me get down to that case first, right? So if I gave you an eigenvalue matrix and you have one positive and one negative, then that means you're looking at a case where it's up in one direction and down in the other. And of course, this generalizes to more values as well, right? The idea is if I give you a 3x3 matrix, all of the eigenvalues have to be positive to be a local minimum. All of them have to be negative to be a local maximum. And if you have any alternation at all, you're at a saddle point. Some directions point up, some directions point down. There is no local maximum. So this is the sort of saddle point. And then finally, the obnoxious case where, yeah, it says you must do more analysis. What I want you to know about the last case, which is what happens when the determinant of the Hessian is equal to 0? What if this happens? Which is the same thing as saying, what if one of the eigenvalues is 0? When does this happen? So I asked you a conceptual question, and I say, for what kind of functions, what would we expect geometrically? What could cause the Hessian to fall apart like this? Where does that typically happen? So asymptotes are one place it can happen. It could fail there. Flatness is what I think about it, right? So yeah, like not just a plane, but what even it's like approaching a plane, but like a quadratic or something. So the example to keep in mind when you're thinking about why the second derivative test fails is the example of the second derivative test cannot tell you the difference between this function and this one. If you go through the process of what you learn in calculus and you try to say what's happening at the only critical point this function has. This function has a critical point at 0. How do you find it? You take the derivative and you set it equal to 0. And what you'll find is for both of these functions, 0 is a critical point for both. Why can't the second derivative tell you if you're at a local maximum or a local minimum? Well, you just naively compute it, and what you'll find is that f prime prime of 0 is equal to 0. F1 prime prime of 0 is 0 because f prime prime 1 of x is equal to 6x, and f prime prime 2 of 0 is also equal to 0 because f2 double prime of x is equal to 6x squared. So the second derivative test tells you nothing. And the reason it tells you nothing is because these functions come to the axis too fast. This is way flatter than a parabola, right? Parabolas like touch once and then leap away. This function stays kind of squished down on the axis for a while, which is why the second derivative test fails. And then likewise, x to the fourth comes in and is like a really flat parabola before it shoots off to infinity very quickly. The same situation is true in several variables. So if you look at something like this, even a function that obviously has a minimum someplace, like this one, this function obviously has its minimum value at 0, 0. It's like a hyperparaboloid looking thing, right? But the problem is it's so flat on the bottom that the Hessian is going to be 0. Now that's the sort of question where I could say, compute the Hessian of this thing at 0, then you do it and you realize, oh, geez, the Hessian is nothing. And then I say it doesn't have a maximum or minimum, and then you have to think for a second, right? That's not further analysis. It's like there's no math to do there in the sense of computation, but there is math to do in the sense of what does that actually look like? And the answer is it's like a really, 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 really flat looking paraboloid. And the reason the Hessian fails is because it's so flat.
So just to make sure on a question like this, like obviously we're going to still have to find the critical point. You're just going to give us diagonal matrix spreads.
I'm going to give you like either a diagonal matrix representation or a diagonal matrix you could plug the numbers into to figure out the eigenvalues.
Okay, it's going to be just like random points then, so we have to know which one.
No, I mean the ideal would be if I tell you a function that you plug numbers into. But yeah, basically like the worst case scenario is I give you either a table that says for this a value, these are what the eigenvalues are, Or I just write down, here's the matrix and here's what the matrix would look like. Here's A, here's what the matrix looks like. Okay. So
So
you-
where's the second option?
What's that?
Could you elaborate? Second
Yeah, so
option?
either it'll look like this, it'll say, you'll have a table that looks like A,
No, that's
and
the
then
eigenvalue.
eigenvalues of A. So this is one option where A is 0, 0, and then I tell you the eigenvalues of lambda 1 is 0, lambda 2 is 0. And to be able to interpret from that. The other possibility is that I write something where A is 0, 0. And then I tell you HF at A, it like diagonalizes to, say, I don't know, 1, 0, 0, minus 2.
Oh, okay.
Right,
Yeah.
either this option or that option. It's going to be one of the two. This is not intended to trick anybody. It's just, I'm sure this is trying to drive home the idea that this is a matrix and the matrix diagonalizes to this. I mean, this is the same, this is not the same information. It would be, if we put a 1 and a 2 right here and a 1 and a 2 right here. This is the same information. Telling you that these are the eigenvalues is the same as telling you that HFA diagonalizes to this. What else? Yep,
Would you mind re-explaining the concept of scalar and vector line?
sure. Okay, so you mean like what they mean? Okay. So, of course, your first task, if I ask you to compute a scalar line integral, is to be able to write down the formula from the formula sheet of identifying which one is the scalar line integral. And I know that seems like an insulting thing to say to you guys, but in the heat of an exam, many a person has written down the wrong formula for an exercise, right? So if I say vector line integral, you have to be able to look at that sheet and identify which one is the vector line integral. The vector line integral looks like this. The integral over C of f dot ds. You know it's a vector line integral because this has a vector inside of it, right? The formula itself is built from vectors. I can't even use a dot product unless vectors are involved. So vector line integrals are hinted at by the fact that the ds term is equal to, it has a vector sign on top of it. And what you're supposed to know about this, actually, in the formula that I wrote up, is that I actually write down that this is equal to the integral from A to B of f of x of t dotted with x prime of t dt. Is that actually written? Yeah. Did I write the mdx ndy form? Ah, so that's your job, apparently. This is also equal to, in the two variable case. The reason I can't put this in the formula sheet is because this is only true in two variables, right? In two variables, another way of writing it, so if we're in R2, this is also equal to the integral of mdx plus n dy. In three variables, this is also equal to the integral of mdx plus n dy plus p dz. Now, you don't need these formulas. You just need to be able to recognize them, right? But all of these are vector integrals. Now, how do you interpret what a vector integral is doing? So a vector integral can be said to be computing work. That's the basic interpretation of what a vector line integral is doing. So a vector line integral, the easiest way to interpret a vector line integral is work done by force F on a particle traveling on X. Yeah, I mean, that's what a vector line integral is, right? And the way that you would picture that, it's like this. You got some object moving around, there's its path, x of t. If you pick some point in time, there's a derivative here, which is x prime of t. And then there's a force, some sort of vector field surrounding it where, you know, there's field lines, field lines, field lines. I think I told you guys that if I gave you a vector, if I wanted you to analyze a vector field, I'd draw a picture of the vector field, right? So no hand drawing vector fields on here, unless you really want. So what you're computing when you do this is the dot product between these two vectors, which means you're picking up how much of f points in the direction of motion of the path. And then essentially what you're saying is, well, the force moved, you know, as the object moved in this direction a little tiny bit, this is the force that was applied, which is a work quantity. So it's like infinitesimal work. That's how you interpret a vector line integral. Easiest way to interpret it. A scalar line integral. Man, this class has a lot of stuff. A scalar line integral means, well, we don't have a vector ds, we have scalar ds. What does that look like? Integral over C of f ds, little f to specify it is not a vector field, it's a scalar field. It's a scalar function f multiplied by the scalar version of ds. And that's equal to the integral from a to b of f of x of t times the length of x prime of t dt. Because that's the ds substitution that you need to remember. And how do you interpret this? The easiest way to interpret a scalar line, I think anyway, the easiest way to interpret a scalar line integral is wow, man. All right. If f is equal to, so say like one interpretation that's really easy to remember is that if f is mass density, if f is a function that assigns mass density, so you give me a point, I tell you what the density of some material is at that point, then the integral from a to b of f of x of t, sorry, this is supposed to be, f, times the length of x prime of t dt, or really, I guess ds is the easiest way to think about this, f ds. This is equal to the total mass of the curve. That's one way of thinking about it. You got some curve traveling through space. You cut it up into pieces. Each piece is delta s long. I tell you what the density is in that piece, and density times length is equal to mass. And then you add all the little masses up and you get big mass. That's, to me, that's the easiest interpretation of what a scalar line integral is. Another, I apologize. I know somebody told me no physics earlier. Somebody was like, no physics. I wasn't in here. I think somebody was yelling at me in 306 about like never mentioning physics. But I was on 306, and I was a graduate student, so it's even worse. The other way that you can interpret a scalar line integral is you can imagine that you have, you can imagine that you have a path, say, sitting in R2. So this is a curve contained in R2. It's the easiest way to visualize this. And it's the shadow of a roller coaster. So the sun is shining straight down, and on top of this path, there's a roller coaster that's moving along this path. So the roller coaster twists, it doesn't go straight up and down. The roller coaster is sort of curving along with the path that's underneath it. And another way to interpret what this is giving you is it's the area contained underneath the roller coaster. I know roller coaster is a weird analogy, but it's like, it's the section of a three-dimensional surface that's cut through by the curve C. Like, it's kind of a harder thing to say. Yep. So this is C down here, and this is F. And the thing is that what the X does is the X is a particular parameterization of how you travel down the path. And the point is this quantity should not matter, right? With this type of integral, it shouldn't matter how you parameterize the path as long as you are always moving forward. The area should be the same no matter what you do. That's why this is a DS integral, right? DS says this is in terms of arc length, which means like the X is just some way of describing how you travel down the path. That's what the X would be in this analogy. Riemann, yeah, Riemann and Darboux both, right? I'm not sure that the roller coasters of the day of Riemann would have been very safe to be on. But that doesn't mean they didn't try anyway. You've seen some of the world's exposition stuff they built out of galvanized iron. You really want to see some bizarre contraptions like people wrote in the 1800s. Go look at some of the stuff that showed up at the Chicago World's Fair. Oh, yeah. The really amazing ones are the ones that were like the machines that would shock you if you touched them wrong. All right, so okay here. Remember, the idea of this test is not to trick you and it's not to destroy you. It's to just cover the material we did, right? The really hard stuff is not on this test, which is Green's and Stokes theorem, and divergence theorem. And that's like that's the real meat of the class. And so that's what we're doing next week. We're going to finish it up with a 3D version of the Stokes theorem and the divergence theorem. All right, see dudes.